Hi there, everybody. We're now in our last groundwork on the fundamental theorem of arithmetic. So right after this video, we are all ready, okay, to, we're all ready, okay, to prove the fundamental theorem of arithmetic. Okay, we're all ready then. Okay, so this video will be quite short because the proof of this is quite straightforward, provided you have watched the two previous lemmas we have talked about. So this the lemma 2 has the following result that follows. This is the result, rather, the corollary. This is the result that follows nicely from the lemma number 2. So let's read it. Let's have it. So what does it say? So if P, Q sub 1, Q sub 2 up until Q sub n are all primes, if they are all primes, such that P divides the product of all Q's, shall we say, Q sub 1, Q sub 2 up until Q sub n. So P is divisible by this product, which is a product of primes. Then we say that P is equal to Q sub I for some I, which this I is between 1 and n. Okay? So we say that P is equal to Q sub I. So let's give a proof for this corollary. Let's go back to that later. So let's write proof. Okay, so since we say that since we say that P divides Q sub 1 times Q sub 2 up until Q sub n. Okay, so by lemma 2, so recall lemma 2. If you want, we can give the lemma here. Um, okay, so let's give it for the sake of everybody. So recall, let's recall. This is lemma 2. Okay, it states that let P be a prime. And P divides a sub 1 times a sub 2 up until a sub n, where a sub 1, a sub 2 up until a sub n are all positive integers. Then we say P divides a sub I for some I where I lies between 1 and n. Okay, so that's our lemma 2. We will be using that in this. So the main takeaway here is that we have a P which is a prime, and it divides this product of positive integers, which surely says that this is a positive integer. So therefore, we can pick up one factor of this product, and that factor is still going to be divisible by P. Okay, still going to be divisible by P. So using that consequence of that lemma, so since P is a factor of Q sub 1, Q sub 2, Q sub n, so by lemma 2, there is a certain Q sub I lying here. There's a certain Q sub I here. Okay, Q sub I, wherein P is divisible or is a factor of that Q sub I. Okay, I hope you got it, what I mean by the lemma 2. So by that Q sub I, so therefore P oops, P divides some certain Q sub I. Okay, for some I. For some I, okay, between, n and 1. So where I is between n and 1. Okay, so what we say, but, notice, but, we say from our first statement that all of these are prime numbers. All of these are prime numbers. But we say that P and Q sub I are primes. P and Q sub I are primes. So since they are prime, so Q sub I is a prime number, P is also a prime number, so that's gonna be invisible for them that P is divisible by I by if they are primes. So there's no other way to make sure that P divides Q sub I other than making them equal. Okay, so there's no other way in than make there's no other way rather than making them equal. So if, for example, 2 divides 2, that's correct. 3 divides 3. Okay, 5 divides 7, or rather 5 divides 5, 7 divides 7, but it cannot be 2 divides 7. It cannot be 3 divides 11. So that's impossibility. Okay, if they are different primes, meaning they are equal. Okay, meaning they are equal. So this is the end of this video. This is a short video for this corollary from theorem 2. Actually, right after this, we are now ready to state and establish the fundamental theorem of arithmetic. So it is the most fundamental result actually in number theory. Okay, so the proof for the fundamental theorem of arithmetic will be stated in the next video. So stay tuned and don't forget to like and subscribe. And yeah, I'll see you soon in the next video. Thank you.